Hello, everyone, and welcome to DIPY Workshop 2021. My name is Serge Coudreau, and I'm one of the core developers of DIPY. I also am the release manager of the project. This part 3, this is a part 3 of image registration session. If you have not seen the part 1 and the part 2, I recommend you to start with it because I will skip many concepts. In this part, we will focus on non-rigid or non-linear registration. Here, an example of a non-rigid registration. A non-rigid registration method are capable of aligning images where correspondence cannot be achieved without a localized deformation. So as you can see, here, each region are locally deformed, like we are scratching a paper to obtain the specific field that we want. So this kind of deformation is better to accommodate anatomical, physiological, and pathological variability between patients. So to remind you what is a non-rigid registration process, here the diagram. So the goal of brain image registration is to compute the transformation phi, such as I, our image I here, is as similar as possible as our image G here. Of course, we need a similarity metric who will compute who will give a score on how similar are the data. To achieve independence from the image acquisition parameters, the transform need to be done in the physical space here. So for each data, we will need from the grid space to make an interpolation in the physical space to ensure that we compare apple to apple. The first non-rigid registration model was an elastic model. This non-linear image registration, the transformation phi here is usually represented by a deformation field U that we saw previously. And this deformation U assigns a displacement vector at each point X. The classical elastic model is one of the earliest formulations for non-linear image registration, as you can see on this equation here. One important point that we talked about previously is a similarity metric P that will drive our registration process. Also, you should pay attention to the differential operator else that will control the smoothness of your image. Sorry, to control the smoothness of your deformation field. However, the limitation of the solution, also smooth, is not guaranteed to be invertible. And if it was invertible, solutions are not inverse consistent, meaning that the same function used to obtain the optimal transform mapping G to A to I and I to J, the solutions are not inverse to each other. So if we make the transformation between J to I and I to J, we can encounter different results, which we will try to avoid. But to overcome this limitation, we have a new algorithm who was introduced by Christensen in 2001 and improved by Begg in 2005, named the Large Deformation Diffeomorphic Metric Mapping Framework. This is This framework is commonly used in many applications. So they formulate the problem as a flow transformation that satisfies the following equation. So the final diffeomorphism can be obtained by integrating over time. Then DIPY showed that by enforcing the smoothing in V using L, it can be guaranteed diffeomorphism. So these diffeomorphic flows ensure that images are smoothly transformed and their topology preserved. Advance modifies the standard LDDMM formulation to enforce symmetry by splitting the trajectory in two trajectories with opposite direction. So you will see commonly that on all scene algorithm, you will have a mapping forward and a mapping backward of your data. So Advance computes the gradient of the metric only at the midpoint of the trajectory. The smoothness and invertibility is achieved by convolving the gradient with a Gaussian kernel K and scaling it by a small factor epsilon. So at the end, the gradient scene algorithm registers two input images by computing two diffeomorphisms that map the input images toward a common reference domain. So the final diffeomorphism is computed by composing two partial diffeomorphisms. This algorithm can be found in ANS. This is the original implementation. And we have another implementation in DIPY that we did previous years ago. So here, if we come back to our previous diagram, this is the explanation of the symmetric algorithm. So we have our image here, we have our image G, and we are warping in the middle here. And these two warping, we compose these two deformation field to be able to compute our transformation. Here, see below, you can see below the classical algorithm that are available in ANS in DIPY. So this algorithm is consistently ranked on the top performer along a lot of studies and comparison. And still today, this is really an effective algorithm, especially for multimodal data. You can see in this video a quick implementation that we have in DIPY and that simulate the diffeomorphic nonlinear registration. So as you can see, after many iterations, we deform our grid smallly in the middle, trying to search the local optimal and the local optimum, sorry, until we reach a stabilization point. If you want to use this algorithm with DIPY, it is available via command line. So as Javier explained on day one, you can have a DIPY command line named DIPY align scene, where you need to define your static images and your moving images. So as you see with the command -h for help, you can get a lot of information about what are the optional parameters that you can what you can feed the algorithm, and etc. So it is really important that you define your static image. Your static image can be a template, and then the moving image. If we look deeper in our optional argument, you can see that this command line lets you access to all advanced parameters to fine-tune the algorithm. So you can have access to the level of iteration. I talk about it in part 2, the metric, which usually we use the cross correlation or the sum square difference. You can fine-tune all the metric with different parameters, and it will help you to apply this algorithm following your application and your data. It is also available via Python coding. So we have a nice tutorial in DIPY, DIPY.org scene registration 3D. One of the most important steps that you need, that's not notified here, but you need to do is to apply the affine registration. This is the essential first step that you need to do before applying a symmetric diffeomorphic registration. This nonlinear registration is quite resource important and can be slow. So applying an affine transformation first could accelerate the process and make your warping faster. So as before, you just need to define a metric and call the symmetric diffeomorphic class and set it up with the metric, the level of iteration, and etc., etc. Then you just call the optimize function, and it will give you the mapping of your data. I hope you enjoy this talk. Thank you for listening. And if you have any question, don't hesitate to contact me through GitHub or through the data accelerator of DIPY workshop. Thank you and bye-bye.